This is 15.1, Properties of Detection of Sound. Today we're going to talk about the Doppler shift. We'll explain how sound's traveling into your ear, and we'll explain what happens when the wave is going to change its pitch or volume. So what happens to the wave when we do those things. So first of all, a sound wave is created by vibrations. When you speak, air comes up through your vocal cords and causes them to vibrate. And this is what creates a pressure wave, and that is what goes to your ears so that you can hear it. Now, when something vibrates, it vibrates towards you, or compresses up the wave, and then away, which kind of spreads out those molecules. So it's made up of high and low density air, which is the wave that they're talking about. Now, once you create this high and low density pressure wave, those high density molecules bump the next molecules, which bump the next molecules, which bump the next molecules. And right behind it is a less density wave. So then the wave behind that is another high density. So then it bumps the molecules as it goes forward. So it travels through the air by using the air. And that's why in space no one can hear you scream, because the molecules are so far apart that they cannot transfer this pressure wave through, because there's no pressure wave. There's no air to create that pressure wave. And it's not all of space, it's just the vacuum parts of space, what we normally think of as space. Things that are not planets or stars or big balls of nebula, cloud. To calculate the speed of sound, we can use this one equation over here on the top, where it says velocity is the wavelength over time. This is the same equation that we used before, this one down here, frequency equals velocity over wavelength, which I like mine as v equals wavelength times f. The top one is wavelength over time. That has to be time for one wavelength, so that would actually be period. Now, sound waves are pressure waves, so they're longitudinal, meaning that they're compression waves, right? They're parallel. So just like my slinky here, when I send a wave pulse through it, that's a compression wave. So that's what a sound wave is. Now, the speed of sound can differ depending on the room temperature. The hotter the gas in the room is, the faster sound can travel, because these molecules, they're vibrating around more. They have more energy. They have more heat energy. And since they're vibrating around more, they can transfer their energy faster. Sound also moves faster through denser mediums. So put your ear next to a train track. You can hear the train coming before you can hear it in the air, because the sound travels faster through the steel than it does through the air. Also, it's going to lose a lot less energy, since those molecules are traveling so fast along the length of the steel instead of through the air where it has to go spherical. Okay, the speed of sound and temperature. As I said before, the hotter the air, the faster it's going to move through it. We can calculate the velocity of the speed of sound through air using this equation, where this is the velocity of the speed of sound at 0 degrees, and then this temperature has to be in Celsius. Most of the time, for most of your equations, we'll use the velocity of sound as 340 degrees. So unless it says otherwise, you can assume this. All right, here's some pictures of some compression waves. Up here we have our slinky. It's not compressed at all, so the air would be fine. Nothing wrong with it, no compressions or anything. So you can see the wave here is nice and flat. It's not even a wave. Then we set up our wave pulse. The first part of it is all densely compact. And you can see as we're drawing the wave, that densely compact, that gives us a large amplitude, or an amplitude above the equilibrium. Then it's going to be spaced out. You can see behind this density here, this densely compact, we have more of a stretched part of the spring. So that is the non-dense part of your wave. And so we end up with a low amplitude. And that would be one whole wave right there, low to high density. And then it repeats. We do another dense spot. And you can see that here on our waves. All right, the next thing I want you guys to be careful of is echoes. There's lots of echo problems in your homework. They're going to talk about sonar, such as bats, echolocation, along with dolphins and whales. The only real difficult part of this, it's not even difficult, it's just a little tricky because people forget, is that when you're trying to find the velocity or the distance from something, most of the time it'll be the distance because you know the speed of sound, and it'll be like it takes 8 seconds to get there and back. Well, if you're drawing a picture, you might remember it. Here's our wall. The sound's going to go there and then come back. So the actual distance of it is going to travel twice that distance. So when you use the distance equation, distance over time to find velocity, make sure you put in 2x. All right, in order to detect sound, and again, you don't really need to write all this stuff. You can just write down the shorthand notes of what I say. For instance, a microphone is going to take the kinetic energy from these vibrating molecules. Depending on the frequency, different discs in the microphone vibrate. That's like when you go to a concert and your heart thumps, right? It's resonating with your heart. The same thing with the microphone, except for it has these really tiny, delicate discs on the inside of it, and each frequency is going to vibrate a different disc. And that vibration turns into electrical impulses in the microphone and then sends it out so that it can send it as electrical energy or electromagnetic waves. Your ear is going to work a little bit differently. It takes the vibrating molecules, those pressure densities. It goes down your ear canal. It hits your eardrum, which is connected to these very tiny bones. And so it takes, even like loud sounds, it's going to take these vibrating bones and make them vibrate. So the more they vibrate, the louder the sound. Now these vibrating bones are very delicate, and they go right into your ear, which is full of this gel. And those vibrations go through the gel, and depending on their frequency, right, how squished up the wave is, or how stretched out the wave is going to set off different nerves. Each one of these nerves is going to vibrate to a different frequency. And if it vibrates, then it's going to send that sound into your brain, and it's going to interpret it as a certain note. So that's the inside of your ear. It looks kind of gross, especially in this picture with all these like little porous things going on here. I don't know if that is burning matter or bone or something. Now, what's interesting is that this is what also causes your balance, right? Your ear is filled with this gel on the inside, so when you turn, that gel moves in your ear, and your eyes move with the gel. So they're like connected to it. They take those impulses and they move. So when you stop moving, your eyes stop moving. This keeps your balance. Now, if you have vertigo, like me, in the inside of your ear, everybody has crystals. Now, if these crystals fall off, like me, you get these like little salt grains in your gel. So when you turn your head, the gel moves, your eyes move, and then the rocks hit, right? The crystals hit, and your eyes keep moving. So they do this. So what happens is you see everything moving like this, and that's what makes you dizzy. Because your brain is interpreting, hey, we're still moving, even though you're not moving. And then you get dizzy. So that's what's happened to me. I've had that for about a year. Not fun. All right. Next thing we're going to talk about is pitch. Pitch is frequency. In case you're not sure what I'm talking about when I say frequency, that's how often the wave goes. So this would be something that's high frequency. This would be something that's low frequency. So something with high frequency is going to be a high note, and something with low frequency is going to be a low note. So each frequency, which you can see up here, we have different frequencies for different notes. These are piano notes up here. And volume. Volume is the size of the wave. So here is a very loud low note. And here is a very high loud note. It's volume, high notes, volume, low note. So the frequency tells you which note it is, how often the waves go. And the amplitude of the wave is going to tell you how loud it is. Now we can detect pressure waves between 2 times 10 to the negative 5 pascals, which is 0 decibels, all the way up to 20 pascals, which is 120 decibels. Now look at the scale here. This is a large range from negative 10 to the negative 5 up to 20, where this one's only 120. So it's a logarithmic scale. When you go up 1 in the decibel level, you're going to go up a log on the, I think it's a magnitude of 10 on your normal intensity pressure wave. And you can see at the top we have very loud things like jet airplanes, car horns, your airport, pretty loud. At 20 pascals, this is pretty painful up here, all this red stuff. That's pretty loud. That's going to hurt your ears. Your bedroom is about 40 decibels. A recording studio where I have all that protection on the walls to keep all the sound out. Something that's silent like that is protected. going to be about 30 decibels. Here's a lovely picture of decibels up here. You have 10 decibels is barely audible, 30 decibels, that's a whisper, all the way up to your jet airplane, 140. Make your ears bleed. All right, the last thing we're going to cover is the Doppler effect. This says that when an object is moving towards you, you hear a higher frequency. And when it's moving away, you hear a lower frequency. This is because the waves become compacted as they get towards you. So imagine a siren. You're sitting in the car and an ambulance goes past you. What do you hear? It goes, boom, right? As it comes towards you, the higher frequency, so you hear a higher note. And as it goes away, a lower frequency. So I have some interesting little animations. This I stole off of Wikipedia, so if you want to look at them again, that's where they are. This is the sound wave coming from a stationary object. So you can see the waves are even on all sides. But when the object starts to move, in the front of it, you see all these piled up waves. Now they pile up, they're also getting closer together, so we end up with a higher frequency or a higher note. And behind, they're starting to get stretched out because the object is moving away, creating a longer wavelength. This is going to be a lower frequency, so you're going to get a lower note from behind. Now, if this object goes as fast as the speed of sound, so here is something that is right at the edge of what they used to call the sound barrier. They used to think you couldn't get over it, and then they did. And they're like, oh, okay. It's not really a barrier. It's just a bunch of compression waves all built up on top of each other. And at this point, it's really turbulent. It's like right at the edge of the wave, and it needs just a little bit more energy to get past those waves. And when it does, it creates a sonic boom. It creates these pressure waves that go out from behind it, and then when they reach your ears, it's all these piled up waves right on top of your ears, so you hear the pop. It's pretty much the same as a shock wave. A shock wave is a pressure wave. So there's no difference between a shock wave and the sonic boom. Other than the fact of what creates it. If you go faster than the speed of sound, so you've made it past this sound barrier, you're allowed to pop your sonic boom, you can see that behind it, still longer waves, and then you get these higher frequency waves right up front. So as it's coming towards you, you're going to hear higher right here, and then lower as it goes past. All right, here's a stationary Doppler shift for you. Behind here we have longer wavelengths, so you're going to have a lower frequency. And in the front, higher frequency, shorter wavelength. But the speed of sound is still the same. Still going to be that 343. Here's the equation for calculating it. The only thing I would have probably changed on this that I didn't is this is like Fs. because some people will get confused with that stuff. So FO is actually FS. I call it F naught because it's like the original frequency, but FS would have been better for this. So this is the frequency of the detector. So this is what U here. And in my last class, I wrote the frequency of U, and people started laughing. So we're going to stick with the detector. It's going to be a little better. This is the frequency of the source, or the original frequency. So what's creating the sound, and that's going to be the source. On the top here, this V naught, that is the speed of sound. That original speed of sound, 343 for the most part. So you can just replace it with 343. On the top, we have the velocity of the detector. So how fast are you going? And on the bottom, we have our velocity of the source. How fast is the thing that's making the noise moving? Now the top will be positive if it's going towards you. Are the things getting closer together? Is it coming at you? So it's going to be positive if it's towards. And if it's away, then the bottom will be positive instead. So you either have positive over negative or negative over positive. Now this is just a simplified version. It really only works when one of the things is 0. We're not going to get more complicated than that. Really, we'll have a couple where they're both moving, but we won't address it. Even though if you did, you actually change it to be relative speeds, which will change your speed of sound. So we're not going to do that. I do that with my AP students. For you guys, just use the equation the way it states it, and it will be okay for this stuff. All right, you guys ready for your practice? You are in a van moving at 24 meters per second, and an ambulance comes up behind you at 30 meters per second. The ambulance's siren rings at 370 hertz. Use the speed of sound to be 343 meters per second. What is the frequency that you hear? Now again, this one, if we did it the AP way, you're actually going to get a different frequency, but for you guys, we're just going to stick with the equation. And it's because both of the things are moving. What we would actually do is shift them so they'd be relative velocity, but we're not going to worry about it. Just going to use it the way it is up there. All right, so we have 24 meters per second, 30 meters per second, 370 hertz, and 343 meters per second. What's this 24 meters per second? What is it? The top V. It is the velocity of the detector. Very good. Or if you want the velocity of U. Detector. Okay, and what's the 30 meters per second? Vs, the velocity of the source. And 370 hertz? Say it louder. Frequency of the source, or the FO. And then 343. Very lively this Monday morning. The VO, the velocity of sound. So that's already in our equation up here, so we don't actually need to write it. That's fine. Okay, let's plug in our numbers. We're looking for, what do you hear? Detector. Keep doing it. Can't spell it. Okay. Frequency of your detector, frequency that you're going to hear, frequency of the source is 370. We got this 343. Running out of board space here. Over 343. So, is it getting closer together or is it getting further away? Say louder. Closer. We're getting closer together. So, it's going towards each other. So, we have positive on top, negative on bottom. And you are going 24, and the van is going 30. Ooh. So let's put this in our calculator. If I remember correctly. If I remember what the number is. 370, and I think this is 1.1 something. Let me double check that. 1.17, there we go, times 370, 434 meters, or let's see, hertz, there we go. So that's our frequency that we hear. Now, does it make sense that it's higher? Yeah, it makes sense because it's getting closer together, so it's smashing up those waves, and it's getting higher. All right, we have some clicker questions for you today. Here's the first one. How does sound travel from its source to your ear? You give it a second. Here's your clicker. It's on.